Singing has been outstanding, so appreciate those who've led and the way you've participated in that, because we want to declare God's majesty every way we can, don't we? Amen. All right, we're going to begin our lesson here shortly, but I have to say a few things first by way of introduction. First, I want to thank again the elders for the invitation to be here and for their wisdom in having a series like this. I believe it's critically important for our time. And it's as if God has opened the floodgates of information to explain things to us from the natural world that we never knew before, to help young people especially in our time who are being confronted with all kinds of challenges, that there is no God. My hope, of course, is that in the course of this, everyone is overwhelmed with what God has opened to us. So I'm trying really my best to get that across, and I realize when we've finished, we will not have touched the hem of the garment. But I hope we've touched your interest. And there's a bibliography in the back. If you want to study further, there's so much good material today. When I was in Harvard University studying in the 1960s, I couldn't find anything worth reading by creationists. I'm sorry, but that was the case. And that's not the case anymore. There's lots of powerfully good material written by respectable scientists who treat this and then show you what it points to in terms of the God of this universe. Now, some other things. Several of you have taken care of me really well this week. My Marilyn sends her special love to all of you who fed me and entertained me and visited with me and taken care of me. So thank you so much. It's a joy. And some of you know I've taken notes, right, on all of you, as many as I could, because I want to tell Marilyn all the details so she can get to know you too. You're special people, and we thank God for this church. I also gave an assignment Sunday. You remember, those of you who are members here? And I ask you to bring your manuscripts with you tonight. So, class, we have a bunch of manuscripts up here on the front table, done by several of these people, and I'm going to leave them up here for you to look, but I just give you a little vision here of work that these children have done to make something that looks like a manuscript done in the Middle and Dark Ages by scribes to help give God's word to us today. And so I hope it was a valuable exercise. Families that had this done, and all you children that did it, congratulations. Good work. And if I may, I want to keep these. Is that all right? Okay. So I have their names on them. You can come up here and take a look at them later. But I'm making a little treasury of manuscripts that have been done by young people all over this country. I think it's a good exercise because we do need to appreciate the fact that we have in our possession the Word of God in such an easy and convenient fashion, and it needs to be a passion of our lives to study it every day and use it to God's glory. All right, I think that's all I wanted to say by way of introduction. Welcome, class. Those of you that are new tonight, you are in my science class tonight. The elders have given me permission to conduct this as a class, so we'll have class interaction, and we'll have you attentive, I hope, the whole time. And if you get a little sleepy, I'm going to make you stand up. And I'm watching you. All right. Our topic tonight is a follow-up to last night. If you weren't here, I'm sorry. Go back and listen to that. It's been recorded. We talked a lot last night about the chemistry of living things. That led into then a discussion tonight about molecular machines. This is a topic, class, that is very current. It wasn't until about 20 years ago that we started uncovering the secrets of molecular machines inside your cells, the cells of every living thing. It's amazing what's going on and what we've learned. So tonight, my goal is to share just enough of that to give you a taste and hopefully for you to investigate further. So thank you for being here. Let's get right into it. This is our theme passage from the Bible, which I always use in a setting like this in a church building, because I think it's appropriate. Most of you are God believers already and believe the Bible's the Word of God. The point of doing this is to show you that the Bible itself teaches that God's attributes can be seen even though He's invisible. And you see them by the things that are made. And so it's the testimony of the argument from design. If you see something that's designed or looks like it's designed, the most logical explanation is it was designed. And in this case, by a grand designer. So the Bible teaches that you can learn about God without the Bible. You got that? That's God's other book. And that's to which I will turn tonight. So I'm not using this book tonight. I'm using His other book. All right, here we go. I introduced this in the first lesson on Monday night, a book that was used very widely in the 1800s in England and in Europe. Otherwise, The Natural Theology, or the Evidences of the Existence and Attributes of Deity Collected from the Appearances of Nature by William Paley. It was a standard work in those days and extremely well done. In fact, Richard Dawkins, who is our modern day critic of belief in God, wrote a book called The Blind Watchmaker in direct response to this. Because the opening pages of this book is an example of the watchmaker argument. If you were here on Monday night, I did that for you in British English. I hope you didn't forget that. I'm not doing it again tonight, but the argument is if you kicked up over a stone and found a watch lying in a heath in England, you would ask, who made that? Not, isn't it interesting how that just came about? Your logical question was, who made that? And then the argument in the book is, in nature we see things much more complicated than a watch all the time and everywhere you look. So they testify that there's a grand watchmaker. That's what Dawkins is writing about. So what I want to do tonight is show you what Dawkins does with that. Dawkins is a professor of biology at Oxford University and has been appointed by that university to be the professor of the public understanding of sciences. He's supposed to tell you common folk what sciences are all about. And if he's the chosen apostle to do that, I'm very sorry about that. Because he's eloquent in some ways, but he's also mean. And he must have had, I just have to believe he had a terrible experience with religious people. Because he's just vicious almost about how terrible religion is and belief in God. So I'm sad about that because that's totally unnecessary. And certainly we don't need to be doing that. But let's turn now to Richard Dawkins. Here's a picture of the man. And I thought I would just take a few pages out of his book here and share it with you. So bear with me and we'll just read just a little bit because I want you to see what he does with this. So I'm turning in the book, The Blind Watchmaker, to page 1. And here's the first sentence. We animals, does that give you a clue? We animals are the most complicated things in the known universe. Would you agree with that, class? I hope so. I think it's right. Then he says, biology is the study of complicated things that give the appearance of having been designed for a purpose. Okay? May I say to you, everybody admits that it sure looks like things have been designed for a purpose everywhere you look. And he says that's what biology is. It's a study of things that sure look like they were designed. And then he spends 300 pages trying to convince you they were not designed. They look like they were, but they weren't. Let's go on. This is page 3. The process by which an airliner came into existence is not fundamentally mysterious to us because humans built it. Would you say amen to that, class? Yeah. The systematic putting together of parts to a purposeful design is something we know and understand, for we've experienced it at first hand. You kids did a great job designing that. And believe me, even if there's mistakes in here, this wasn't made without intelligence and careful consideration and planning. He says we know about that. So what about our bodies? I'm back to quoting him now. Each one of us is a machine, like an airliner, only much more complicated. Were we designed on a drawing board too, and were our parts assembled by a skilled engineer? The answer is no. It is a surprising answer, and we have known and understood it only for a century or so. Charles Darwin first explained the matter. Many people either would not or could not grasp it. I myself flatly refused to believe Darwin's theory when I first heard about it as a child. But you can believe that he now is totally convinced of Darwin's answer to this question. Were you designed? You absolutely were not. I'm now on page 4. The watchmaker of my title is borrowed from a famous treatise by the 18th century theologian William Paley. We just saw it. By the way, I wanted to show you, I have a new edition of that book. It's been reprinted. It would be a nice exercise, parents, for you to spend some time with your children going over some of the chapters of this book. You can buy it now. It's a reprint. Natural Theology by William Paley. It's well done. And listen to what Dawkins says about it. He says, it is the best known exposition of the argument from design, always the most influential of the arguments for the existence of God. It is a book I greatly admire, for in his own time, its author, William Paley, succeeded in doing what I am struggling to do now. He had a point to make, he passionately believed in it, and he spared no effort to ram it home. Folks, have you heard me ram things home? I hope so. I make no excuse for that. Richard Dawkins' book is full of it. And he passionately believes what he's telling you. He's completely wrong, but he believes it with all his heart. He doesn't even want to admit he believes it. He wants to say this is the truth because it's science, and what you folks believe is religion. And he's totally wrong about that too. He had a proper reverence for the complexity of the living world, and he saw that it demands a very special kind of explanation. The only thing he got wrong, and admittedly quite a wrong thing, or a big thing, was the explanation itself. He gave the traditional religious answer to the riddle, but he articulated it more clearly and convincingly than anyone had before. The true explanation is utterly different. It had to wait for one of the most revolutionary thinkers of all time, Charles Darwin. And it's almost like, shall we bow before him? Then he goes on to quote the famous passage in Paley's book about the watchmaker. And then he says this on page 5. Paley's argument is made with passionate sincerity and is informed by the best biological scholarship of his day. But it is wrong, gloriously and utterly wrong. The analogy between a telescope and an eye, between a watch and a living organism, is false. All appearances to the contrary. The only watchmaker in nature is the blind forces of physics, albeit deployed in a very special way. A true watchmaker has foresights. He designs his cogs and springs and plans their interconnections with a future purpose in his mind's eye. Natural selection, the blind, unconscious, automatic process which Darwin discovered and which we now know is the explanation for the existence and apparent purposeful form of all life, has no purpose. It has no mind. It has no mind's eye. It does not plan for the future. It has no vision, no foresight, no sight at all. If it can be said to play the role of a watchmaker in nature, it is the blind watchmaker. So, class, I hope I didn't lose you. Here's a summary of what he says in that article, in that portion of his book. The only watchmaker in nature is the blind forces of physics, albeit deployed in a special way. You don't forget that. The way you got here, living beings, is by this natural process. And it came about by the blind forces of physics. Now, the difference is in his mind. It was operated on by natural selection. The blind, unconscious, automatic process. The blind watchmaker. Folks, Mr. Dawkins and his ilk practically attribute to natural selection the properties of God himself. In their mind, it has the capacity to take what's in nature and develop it from nothing and from non-living things to every living thing on the existence of this earth. That is exactly what they teach. And of course, he thinks we just don't understand natural selection. We just haven't gotten it yet. Well, I have to share with you at least one other thing here. I'm on page 14 now. In his beautifully written book, The Creation, the Oxford physical chemist Peter Atkins begins. Folks, Peter Atkins is a Nobel Prize winning physical chemist at Oxford. I'm reading directly from his book called The Creation. I shall take your mind on a journey. It is a journey of comprehension that takes us to the edge of space, time, and understanding. On it, I shall argue that there is nothing that cannot be understood, and that there's nothing that cannot be explained, and that everything is extraordinarily simple. A great deal of the universe does not need any explanation. Elephants, for instance. I'm pausing there. Elephants don't need explanation. Once molecules have learnt to compete and to create other molecules in their own image, elephants and things resembling elephants will in the due course be found roaming through the countryside. Did you hear what this Nobel Prize just said, Nobel Prize winner? You don't need to explain elephants. All you need is molecules that can reproduce themselves, and you'll get elephants. Whew. If that's what our professional scientists are teaching our students, we're in big trouble, folks. I'm just reading you from the book. I said the first night that I started talking, don't you believe something because I said it. I expect you to check everything I say, and you believe it because you become convinced of yourself that what I've said is the truth. And I'll tell you where I got it. You can go look for yourself. There's a bibliography on the back, and you ask me if you need to. Well, that's how I wanted to start tonight. And here's what he means by natural selection, class. Nature will produce by itself variation. Just look around you. Is there variation among us? Well, we got different sized noses, don't we? different hair, different shapes, all kinds. So nature presents us with variation. And then nature will select those variants which are most likely to survive. And because of that, over time, things change, they evolve. And that process is sufficient to account for all the changes that have ever taken place on Earth. That's basically it. I say that doesn't explain it, folks. And nor does it account for all the things we observe. Nor does it fit with common sense that testifies this has a design. So I say it's time to revisit the argument from design, and that's what I'm doing in this series, and will continue to do the rest of the time God gives me breath, because it's the strongest argument from nature for the existence of God. I've introduced to you from Stephen Meyer's book, The Return of the God Hypothesis, that there have been 3 scientific discoveries in the 20th century that have led us to believe again in design. One is that the universe had a beginning. We're not talking about that one in this series. A second is that the universe and our solar system and Earth were remarkably and are remarkably fine-tuned to support life on Earth and have been since the beginning. We did talk about that one, didn't we, at some length. And thirdly, even the simplest forms of life at the biochemical level contain massive amounts of digital information. And class, we don't know any source of information other than intelligence. And the most logical answer to the existence of massive amounts of information is that it came from an intelligent source. And nature by itself is not an intelligent source. And that intelligence is being used to produce and maintain untold numbers of molecular machines and complex processes, which leads us to our topic tonight. My introduction is finished. Let's let Darwin say something to us. By the way, I brought his book. This is my copy of it, pretty well abused. May I ask how many in this audience have read this book? Like 5 or 6 of you. It's a little tedious to read, I grant you that. But folks, if you're not aware, this book has changed the course of human existence more than any other book except the Bible. It has, because it has changed the way we look at the world and where the world and all its things in it came from. So it's a massively significant book, way more significant than it should be, but it is. But one of the things I like about it is that Darwin in this book critiques his own theory over and over again. He tells you flaws in it and things that would discredit it. And that's a sign of an honest man, I think. And my justification is, and my guess, is that if he were standing here today and listened and learned all the things we're about to talk to you about and all the others that go with it, he would give up his theory, certainly in the general sense, because it doesn't do the job. So here's one of the things he says about his theory. If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down. His theory, class, depends on a sequence of small changes over long periods of time that add up to produce something very complicated. So he's saying here, if you could show me one thing that could not possibly have been formed that way, then I'd give up my theory. Now there's a little problem with that, the way he says that. It's hard to compete with somebody who says that it could not possibly have been. And these guys can make up stories like how things came about better than anybody ever saw. And they are flat out fairy tales. But he said, if you could ever come up with something that you could not possibly explain this way, my theory would break down. So I'd like to introduce to you one. How about this one? The single cell, which to Darwin was a little blob of albuminous carbon. No, class, it's this complex interplay of all kinds of complicated things. In fact, some people in their books that speak to cellular biology say there's more going on in one cell than all the busiest cities in the world together. And they're right. This is incredibly complex, class. And if you think that that thing came about by natural causes, small-scale changes over long periods of time, here's what Dawkins would say to you. He'd say to you, take any part of that you want, and if you say that's too complicated to have happened by natural causes, then just break it down into something less complicated. In other words, reduce it into parts. So maybe it's not this whole thing, but maybe part of that came about, and then part of that, and then part of that, and over years and years and years, it added up to where you are now. And I would just say to you, ladies and gentlemen, how long does it take before you give up on that? And I'm telling you, the cell presents you a massive example of things that could not possibly have been formed by Darwinian evolution. This is a self-replicating nanoscale robot. And why do we say that? Because it reproduces itself automatically. Every piece of it is reproduced. And the reproductions are perfect. And even if there's a flaw sometimes, because there are things that happen, it has built-in ways to fix those flaws for many instances of it. Well, that's a problem for an evolutionist. Second, they're nanoscale at the quite small level, and they can manipulate single molecules. And third, it's a robot because its activities are carried out unconsciously and automatically by precision molecular machines that follow ordinary physical laws. That's what we've learned in the last 20 years. Lots of machines going on, doing all kinds of things, and everybody knows machines are built by intelligent designers. So, may I talk to you about some molecular machines? Your answer is? Yes. Yeah. That wasn't very enthusiastic, but we'll keep trying. So what's a molecular machine? It's a natural device on a molecular scale with few exceptions made of, class? Protein. Oh, that's so good. If you weren't here last night, we said proteins at least 50 times, didn't we? Because they're everywhere and they do important things. These molecular machines are made up mostly of proteins. And they're carrying the weight of the work that's done in your body. And it's happening all the time, right now, in every cell in your body. Able to convert chemical energy to produce linear, that's straight ahead, or rotary motion, that's like this, as well as controlling many biological functions. So there are machines doing all kinds of things for you. And my goal tonight is to introduce you to just a few. May I say to you, class, when I get finished, we'll have talked about 3 or 4. There are thousands. Thousands. All very busy doing things all the time. And the question is, could those molecular machines which keep you alive and which are doing things constantly have come about by natural causes, small-scale changes over millions of years that add up to produce the machines? No, class. The machines need to be functioning, and they're not functioning if you don't have the parts. One is myoglobin. It's the oxygen storage in muscles. I thought about showing you a picture of that one, but I want to focus on something else. It's the first one we discovered. It's a busy machine to keep oxygen in your muscles. These two I want to talk to you about a little bit. It's called the kinesins and the dyneins. Kinesins are involved in cargo movement. They carry stuff. And cell division, which I want to talk to you about tonight. The dyneins are involved with the beating of cilia and flagella and in cell division and lots of other things, as you will see. So we're going to talk about those a little bit tonight. In fact, if I had gotten here a little earlier, I was going to hope to get you to get on a website. Eric, are you saying you could still do it?
We try.
Okay, because I'm not going to need you for just a little while. So I'm going to give you a website to look up. We're going to test this man tonight. He's my AV-IT guy, y'all, and he's the best. By the way, you owe him a hug later. The one I'd love for you to pull up live is a day in the life of a Keynesian walker. See the word Keynesian up here?
You want that right now?
If you can. I'm going to keep talking. You see if you can find it. A day in the life of a Keynesian walker. All right, while he's doing that, whoops, what happened here? You gave me a song. I don't want that.
I need to go offline with the PowerPoint for a second.
So you're going to have to go off my PowerPoints? Oh, phooey. All right, well, we can talk a little bit. A Keynesian walker class is a, what do you think? I should have you say it. It is a, yeah, but it's a, what's it made of? Protein. It is a significantly large protein, but it's really not very big. And one of the things the Keynesian walker is known for is that it can walk. Okay, so I'm going to illustrate. It has feet that do this. Okay, literally. They literally do this, and they follow physical laws, just as the definition said a moment ago. We can tell you the chemistry that allows a Keynesian walker to step that foot up and then pick the other one up and step it. I could tell you the chemistry tonight if you wanted to give me another hour. Because we know exactly how that works. And what they do is they walk across a microtubule down this road, and they carry stuff that needs to be transported from one place to another. You think that's an important part of living? It certainly is. Is it back up? Oh, are you at the life of a Keynesian walker?
I've Googled it, and so if you see anything out there that jumps out as correct, it's a website?
Well, I think it's a YouTube. See what I know about this? You know who I get to help me? My grandkids. It's a YouTube video, I believe. Maybe that's the way to search for it. We can't take too long with this.
Yeah.
If you can't find it, it's okay.
You got a motor protein.
Well, yeah, why don't you take that one right there? The Keynesian protein walking on a microtubule. Let's look at that one. I'll get rid of the advertisement. Don't you hate those ads? Oh, here he comes. You see the little guy right here? That's your Keynesian walker. And you see that massive thing he's carrying? These are microtubules. Look at him walking there. You see it? I told you. And this thing he's carrying probably weighs 100,000 times what he weighs. I mean, the guy's busy. And every piece of this that he's carrying is critically important to your life. Because you wouldn't be living if these things didn't happen. So I know that's a picture, but it's a good one, isn't it? Okay, get out of that and see if you can possibly find me, because the little video that's where I'm asking him to show you is a cartoon about a day in his life to show you how busy this little guy is doing his work. And it's really powerful. Did you see a day? There it is, right there. A day in the life of a motor protein. Is this guy good or what? Hogan Rod Lab presents. That's an ad. Get rid of it. Don't you hate the ads that got to go with everything? think you can eliminate that. I'm not sure.
Oh, this is the video.
Oh, is this the video? Well, that's not the one I'm looking for, if that's it. All right. We're going to have to give up on that because I got to go on. Get me back to my PowerPoints. But you can go home and find it eventually. Here's my picture of it. There's the Keynesian walker, and that's the stuff he's carrying on the microtubules. You've seen probably a little better picture of that now. So now, class, I want to take you to a real life situation where Keynesian walkers are doing some of the work. So let's start this way. This picture that I'm about to show you is a picture of mitosis. Now, everybody that's had biology studied mitosis. Please tell me you have heard this before. All right. You know that mitosis is a process of cell division that is asexual. It just is one cell breaking up and to form two exact copies of itself. Okay? This part of it is showing you one where it's already made the copy and now it's dividing. That's what we're going to be watching. So first I have a question for you, class. How many times a day do you think mitosis happens in your body of about 30 trillion cells? How many times a day do you think you are mitosing, if that's a verb? You want to take a guess? I mean, somebody take a guess. Give me a number. 30 million. 60 trillion. Well, no, that's more than the number of cells you have. He said 30 million. That's not even close. It's 330 billion times per day you have this going on. That's with a B. 330 billion times. Well, I've done a little more research on that to get you a little more detail. 86% of that is blood cells, mostly erythrocytes, red blood cells. Your body's making red blood cells like crazy all the time because they're destroyed quickly. They don't last very long. And then another big piece is neutrophils, which is white blood cells. 12% is gastrointestinal epithelial cells. That's inside your intestines. It's rebuilding itself constantly, or you'd be dead, class. The third largest is skin cells. That's 1.1% of all this cell division. Well, 1.1% of 330 billion is 3.6 billion per day. You're killing skin cells and they're sloughing off. If you take that down to seconds, that's 42,000 skin cells per second. Girls, you're losing 42,000 skin cells every second. So take your bath. If you don't think of any other reasons to take a bath, you're sloughing off 42,000 skin cells every second. Don't get stuck with that. They start smelling. That is a fact, class. That came from biologists Roger Sindern and Rod Rodley of Weizmann Institute of Science in Israel. Very recent data on a 20 to 30-year-old man, 154 pounds, 5'7". So you fit in there somewhere. But believe me, class, when I tell you sitting here tonight, you've been mitosing all over the place. So what I'm about to show you is what's going on all the time, and the only way it can happen is with the help of machines. So let's go. We're going to start this video, and Eric is going to stop and start it at my command. So go, Eric. What you're watching here is the nuclear material of a cell. This is the genes, the chromosomes. All of you know about that. And so they've already been copied, and now they're dividing up as you watch this take place. You can see that there are various phases of this, and then they start separating. Here they go. This is the one copy, and this is the other exact copy, and from one cell with all this activity taking place, stop right there, you've now just produced two cells that are exactly identical. Class, this video does not show you the copying of the DNA. Do you think that's important? it's only the most important thing going to happen inside of you, because DNA is what directs everything. The copy has to be exactly right, or you will be exactly messed up. And that happens constantly. And the copies are amazingly accurate. And from one cell, you get two that are identical to the previous cells. It's utterly amazing. Let us keep going. They're going to start over now. So we start again with one cell, and this is the nuclear material. This time we're going to focus in on one chromosome right in here. That one, you see it? Stop right there, Eric. Can you see, class, that there's already two copies? There's one in the front and one in the back. Can you see that? Okay, so the copy's already been made. I'm sorry that he doesn't include that in the video. It's an amazing process, how it copies itself. But it's already done. So the job we're looking at here in mitosis is how do you take those two and in the other, how many chromosomes in a human? 46. 23 from the woman and 23 from the man, right? So there's 46 of these. This is just one we're focusing in on. How does it split those two apart and make two identical cells? What's what we're going to work at. So let's now focus in on this. Keep going. You see these microtubules coming out here? We'll talk about that in a minute. There are already two copies of the DNA right there. And we're going to focus in on this reddish area called the kinetochore. Kinetic means active. This is the core where the action takes place that allows these things to split apart. And that's what we're going to focus in on as we look at a giant, stop right there just a second. This is a giant molecular machine that controls chromosome movement. The movement that allows you to separate those into two cells. That's all we're talking about right here. And now we're going to go down inside here and take a look. So let's go. Okay, the reason he's colored it red is because we're trying to focus on it. That's the kinetochore, and we're going to go right in there and look. See all that activity taking place? These are the microtubules. Stop right there just a second. The microtubules are being constructed down here with the help of, what do you think, class? Yes. And this is mostly proteins here, and it's so these are highways being built that allow that to take place. And way over here at the other end of those microtubules, they're tearing them down as fast as they can build them, like any good government. Right? No, in this case, you have to tear down the microtubules when you get finished, or the cell would get so clogged up with highways it couldn't function. And what do you think it does with the broken down microtubules? It recycles them perfectly, better than any recycling system any human ever devised. So that's happening all the time. All right, keep going. So a lot of other things taking place here. You see all the activity in here, most of it involving, what do you think? Proteins. Now you're going to watch here, and he's got this colored red, and this is Drew Berry, you remember? Red means stop. And so when it's ready to go, he's going to make everything turn green. It does not turn green, class. He does that to identify the fact that it's timed here. Stop right there just a minute. Can you see it's starting to turn green here? What's happening is the proteins are identifying that everything is in place now for the separation to start happening. And that is all timed out by the, that was weak. This is all timed out by the, that's right. Let's keep going. Once the time is right, you're going to start seeing these walkers. The dyneins are going this way, and the kinesins are going this way. Here come the dynein walkers. You see them? And they're carrying. You see this guy stepping? Stop right there just a second. This guy has 3 feet. He's pretty good. But notice all this glob. What do you think that glob is, class? Proteins that it is carrying this way for a particular purpose. What do you think these guys here are? Yes, of course. They're proteins, and right there is a kinesin walker heading that way, and that one's. The ones that are going this way are kinesins, dyneins are going this way. That's the way it is. Dyneins go one direction, kinesins go the other direction, and they're each doing very important specific tasks. Keep going. I just love watching them walk. There goes one of the Kenesans. See him up there? He's feisty. All right. That all, by the way, stop just a second. That was way too slow, class. Have I said that a few times in these videos? That's going way faster than that. Things happen at such an amazing speed, and nobody runs into somebody. It's unbelievable. So much is going on, and it's all happening smoothly. Now we're back up at the larger scenario, and we're going to watch now as this actual separation takes place. But you know what you couldn't see before is down inside here, there's all kinds of machines. You think I've told you the full story? I hope not. There's a whole lot more going on. Keep going. The timing is right, and everybody's functioning as they should, and the red turns green, and the separation takes place in only one of the most important processes that happens in every living thing to keep it alive. And there's all kinds of machines involving making that happen. Well, I don't know how many billion times that happened while we were just talking there, but it's a bunch. And there's machines involved in every step of the way. All right. We've talked a little bit about Kenesan and Dining walkers. Let's talk just a moment about cilia. Kids, you know what a cilia is? Kids? A cilia, any of you older folks know what a cilia is? It's a hair. Typically, it's a hair inside your body. You do know you have hairs all over you, right? Not just outside. And I don't want to talk about some of them. That's not the purpose of this class. But I would like to talk about this one. Right there, you see when you're coming into your lung right here? The primary bronchus, it is covered up with those right there. There are lots of cilia right there inside your lung. For what purpose, class? Is that important to your life? Yes. Why? It filters things out that don't need to be in your lungs. That's why you need to quit smoking, among other things. So class, there are books written about cilia, hairs. You say, that's a boring book. No, we have learned how hairs are built. Every one of those cilia is constructed from the bottom up. They're built. And the little guys that carry it out to the edge, what do you think they are? The Kenesan walkers. And they're Dinings carrying stuff back as you build cilia. It's a complex process for every single hair in your body. And you know, the Lord says He knows every hair in your head. He also knows every hair in your body, and it's being constructed all the time by molecular machines. And we don't have the time to even begin to touch, to think about starting to talk about hairs. So I apologize. You just got to know. That's another one of those critically important things. The one I want to focus in on tonight as I close is a bacterial flagellum. A flagellum is a tail that turns. It's called a rotary filament. And we're going to focus in on one little bacteria. And the reason we are is because it's the most studied little creature on the face of the earth. And the reason for that is it's Escherichia coli. Anybody recognize that? Shorthand is E. coli. Tell me why that's an important thing. If you get it in your food, it can kill you. And if you'll turn your thumb sideways and look at the width of your thumbnail, you could fit 1,000 E. coli across the width of that thumbnail. Is that tiny? Yeah. Little tiny bacteria, one-celled organism. It has a tail. The reason it's studied so much is because it can kill you. We want to know everything there is to know about it because it's an omnipresent type creature. The second reason is there are good E. coli. May I make a case for them? You have millions of them in your intestines, and they keep you alive. They are not you, but you better have them or you're dead. Did you know this, class? You have millions of them swimming around in your intestines as we speak. Sorry, it's not a very nice subject to talk about, but it is the case. And they are critically important to your biome. So E. coli are wonderfully important to study on both sides, good and evil. And we want to know everything there is to know about it. So we've learned a lot about this little guy. So I have a video. Eric is ready to go. And the problem with this video was not built by Drew Berry. It was built by a Jewish company, and it gives us fits. So we're going to see if we can get through this tonight. But let's start it, Eric. Here we go. What you see is a picture of some little swimming bacteria. This is a particular kind of bacteria. They're doing a pretty good job. But next you're going to see the E. coli come swimming in here. Watch these guys. You see how fast they are? Stop right there just a second. Each of those guys has anywhere from 4 to 10 flagellum coming out the back. And those things wrap around each other, and then they go like this, and they drive that thing fast. Folks, E. coli can swim faster than a cheetah can run. The statistics say, let me get it here. I can't remember all this stuff. Single-celled E. coli has 4 to 10 flagella. It's swimming in your intestines at all times. Howard Berg, Harvard biophysicist, has called it the most efficient machine in the universe. It uses almost no energy to make it do all this stuff. The motor which drives that filament turns anywhere from 6,000 to 17,000 revolutions per minute. Now, I did this not long ago in an audience where we had a guy that was into race cars. Any of you into race cars? He told me that in the best race cars on earth produced by humans, the fastest one is 15,000 revolutions per minute. This little motor goes up to 17,000 revolutions per minute in this little bacteria. There is no human machine that touches it. None of them. That means the filament itself is driven anywhere from 200 to 1,000 revolutions per minute, or 17 times per second. Watch me, kids. It's like this. And here's the phenomenal thing. I finish with this in terms of statistics. It can be going that fast in clockwise direction and instantaneously reverse directions up to that speed almost in no time. And what that does is it makes the little guy go this way or this way as he's swimming. There isn't a machine humans have invented that can touch top, side, or bottom of this little guy. It travels 60 cell lengths per second. A cheetah travels 25 body lengths per second. So I say he's faster than a cheetah. But there's something even more incredible that I'm going to conclude with, as you'll see in a moment. All right, you've seen him swim. Now we're going to focus in, because he's too small really to examine him, so we have to have an animation. So here we go. Here comes the animation part. This is the Escherichia coli. It doesn't look like that exactly, but this is the flagellum coming in here, and it hooks up to the cell wall, you see right there. In just a second, we're going to stop, Peter. Eric, so be ready in just a second. The filament is up here. Stop, right there. Okay, this is called the hook. Can you see that that's a different color right there? Class, say something. Okay, the reason it's a different color because that's a different, what do you think? Protein. This is also a different color, so that's a second protein. This is also a different color, so that's a third protein. This is called filament, which is the protein that makes the filament itself. These are the two that allow you to connect that filament to this. This is the hook, and what do you think that is? Made up of? Proteins of a different kind. Class, that hook that connects the filament to the cell wall has to be exactly 52 nanometers long or it doesn't work. How does that happen? I ask you, how does that happen? Yeah, of course, proteins. The proteins time it so that you make exactly the right number of proteins in that stack to make 52 nanometers. And then it stops. And there's no straw boss saying, stop! No, it's guided by the DNA and the proteins. Yeah. Looks like a plan to me. And a design. So we have the filament, the connecting proteins, and the hook. Let's go on. Now we're going to go down inside. See, there's the cell wall, and here are the various rings, and here's the basal body of this machine. We're going to look at the various parts of it here in just a second. There's the rod going up through the middle, and here are all these rings, and there are the membranes. Stop right there just a second. The membranes, folks, the membranes, that's the skin of this little guy. I told you how little he is. Do you know he has skin? And the skin has 3 layers. There's an outer layer, and peptidoglycan layer, and an inner membrane that divide up. And do you see this? See these little stobs right here? They are mounted in the middle layer to give this stability. You know why I made you look at me when it was rotating? Because do you think, folks, when it rotates, it might vibrate a little bit? Well, it'll shake this thing to death. But built into the motor is the stator, that's what it's called, that stabilizes it so that it doesn't vibrate to death. Any rotary motor that any human's ever built always has a stator. Of course, this was done long before humans thought of anything like that. And it's in one of the smallest living creatures there is. And it's working very fine, by the way, thank you. So you've got all these rings and the rods, and we're going to talk about that again in just a moment. Let's go on. Down here you see the motor itself, which drives that machine. And here's the picture of the stator that I just described to you as it stabilizes. In addition to that, the energy source happens right in here. And this is the motor body. Okay, stop right there. Now, here's what the Japanese authors of this video wanted to get across to you. Listen to me closely. Bacteria divide, much like mitosis. It's not exactly the same, but it's similar. They divide, and so from 1 you get 2. When they divide, class, we have learned it does not copy the flagellum. So the new bacteria that are formed have to build a new flagellum. So there's a process built into these little creatures that starts at the bottom with the motor and that builds that entire flagellum all over again. And it takes it about 20 minutes to build a new flagellum. Class, can I get across to you? The process by which this happens is very much like building a tower on a college campus. So you start with the foundation, do you not? And you lay that and carefully design that. And then you construct the next piece and the next piece as you build your way all the way up to the bell tower. Is it important, the sequence of events? Is it important that you have the right materials at the right time in the right place, brought in by somebody and managed by somebody to build a tower? This thing does it by itself. I want you to watch. They're going to show you how a bacterial flagellum and motor are constructed in the cell when it divides. Here we go. I hope. All right, here we go. We're going to start with this set of 26 copies of Fly F protein, and it makes the MS ring right there. Isn't that gorgeous? That's done first. Next is the Fly G protein, 26 copies of that constructed directly underneath. It is not green, class. And then the next one is a combination of the, stop, that went past something, but this is two different proteins built together, 26 copies of each to make the base of that motor. And then next you build the rod, which comes up, which is also a separate protein. Every one of these is different proteins, you get it? And they each have their specific purpose. If you get this protein mixed up down there, you're going to mess the whole thing up. And it has to be in the order that was constructed. And they have to be brought in and provided and make sure the proper material's in the right place at the right time. Keep going. Here comes the rod, and it has a cap now. And the reason it has a cap here is because it's got to drill a hole through the cell wall of that poor little bacteria. Do you think it's healthy to drive a hole through a cell wall? No, class, that would kill him. So I want you to watch. See what happens? Stop. As that hole is being drilled, these rings form instantaneously at the same time to close up the hole and guard it. I have to tell you something else here. I'm leaving out, I'm leaving out 15 things. But I can't leave this one out. See that particular protein right there? What we've learned is that protein would not come to the right place unless it had a chaperone. And guess what the chaperone is? Exactly right. Class. For this particular one, there's a chaperone that directs that protein, 26 copies, up to this end and puts it in place at precisely the right time to close up that hole. And then that particular cap, let's just watch. Keep going. There's the L and the P rings. Is dismissed. Stop right there. Did you see how I just dismissed that cap? Every time something's dismissed, class, it's recycled. So it can be used again. Now we have a new cap. What's this cap for? This is the cap to construct the hook, which gets you exactly 52 nanometers. Watch. See how it guides those hook proteins? And then you dismiss this cap. And you bring up these two different proteins that allow the different proteins to fit together. And then you bring up the center for the final cap. I want you to notice there's 1, 2, 3, 4, 5. Stop right there. This is called the filament cap, and it's so amazing it's been given its own name. This one is called Twinkle Toes. Twinkle Toes. And if you'll watch in a little bit, you're going to see that what she does, if I may call her Twinkle Toes, she lifts one foot, and as she lifts that foot, one protein comes up through that hole and is directed in a specific place. Then she picks up the second of her 5 feet, and another one comes up in exactly the next hole. And then she picks up the third foot, and the next one comes up, and so on. And that continues 32,000 times. So she's really doing this. That wasn't nearly as good as she is. Let's watch. By the way, you're doing great back there. I don't know what you're doing, but you're having magic. See all those proteins coming in one at a time? This is way too slow. They're trying to get you to see what's happening first. See those little feet? And each protein has been put in place. Look, that filament is an amazing protein. It is the perfect protein for a filament because it's tough, it's strong, it's intertwined, it's also flexible. Everything you need for a filament is perfect. And it's about, what, 20 times as long as the little bacteria itself? Class, you understand what I've just told you? Not only does it have the most amazing motor in the universe. So let's just say that was a Ford motor. If you don't like Fords, forget it. It's the best Ford motor in the universe. But also inside this little guy is the Ford factory that builds it. Did you get this? And there isn't a straw boss anywhere to be seen. This is a multiple protein process in every case. Each protein is complex and suited for its function. May I say, designed for its function? Each machine is highly sophisticated, intricate, dynamic, and elegant. And these machines are spontaneously self-assembled in the cell. So you not only have the most fantastic machine in the universe, you have it being constructed by itself in the cell. And there are thousands of them in every living cell. Which is the more reasonable explanation for molecular machines? They were produced by the blind forces of physics through numerous successive slight modifications produced by random variation acted upon by natural selection. That's Dawkins' answer. That is the biggest fairy tale in the history of mankind, ladies and gentlemen. I say a much more reasonable solution is they were designed by a supremely intelligent grand designer. Now let me make this clear. Science cannot prove God. Neither can it disprove God. Science cannot investigate the supernatural. Science can only deal with the natural world. And that, for some scientists, rules out God, period. And I say, no. Science can examine the natural world for all kinds of evidence that points to a supernatural designer. That is not unscientific. And in fact, I would tell you that what God has done for us in this century is He has opened up the floodgates of natural world evidence. There must be a grand designer. But it's a matter of faith, class, ultimately, as is any position on origins. You remember what Hebrews 11 says? Verse 6? Without faith, it is impossible to please God. For he that comes to God must believe that He is, and that He's a rewarder of those who diligently seek Him. It will never be the case where nature by itself will absolutely prove it so certainly that there doesn't have to be belief involved. But there also has to be belief involved in what Mr. Dawkins is trying to teach you. In fact, so much faith, I haven't seen that much faith in all of Israel. I love the book. I don't have enough faith to be an atheist. I'd recommend it to you. It's in the bibliography. So is it reasonable to believe in God in this scientific age, class? I say to you, it's never been more reasonable ever in the history of mankind. So go forth from here stupefied about the majestic Creator who made us, and give praise to His holy name. And thank you for your careful attention.